some exercises yesterday. So let me just do a quick recap what we discussed. Okay. Discussed 3-point amplitudes. We saw by explicit solving the 3-point kinematics that there were two solutions. The first solution when all the square brackets were 0. The second solution are all the angle brackets were 0. We can also use kind of graphical notation for the amplitude. So there is an amplitude for some spin particles associated with that. So if all the square brackets are 0, the amplitude is written just in terms of angle brackets. And if we have same spin particles, they corresponded to minus, minus, plus. So for spin S, the formula that we wrote look like this. And the other type, where all the angle brackets are 0, corresponds to plus, plus, minus. And then the expression looks like this. Okay, so we will use this notation when you see, I will call that white vertex. If you draw it on a paper, it would be white in the background. Here on the blackboard, it's not. This is a black vertex. Yeah, of course, everything is flipped here on the blackboard, but this is how it's usually denoted. Okay. Then I left this exercise at the end of yesterday session. If you ask in which theory these are the 3-point amplitudes for spin 1, yeah, so when we look at spin 1, then we wrote Lagrangian for Young-Mills theory and ask if these amplitudes minus, minus, plus, and plus, plus, minus are indeed amplitudes in the Young-Mills theory. And for that, it's indeed true. Yeah. So if you calculate an amplitude in terms of epsilon's polarization vectors and momenta, then you specify your polarizations to be minus, minus, plus, or plus, plus, minus. For any kind of assignments of 1, 2, 3, yeah, it's important that there are just 2 minuses and 1 plus, or 2 pluses, 1 minus. You use the formulas that we had in the lecture for polarization vectors in terms of spinor helicity variables. You land on these expressions. Yeah. Have people tried to do it over the night? Yeah, some of them, okay. Now, there was this puzzle because we could also specify different spin, different helicities. And that was the amplitude when all helicities were minus. Yeah. Then using the same procedure we did yesterday, we would arrive on solving these 3 equations for 3 unknowns and figuring out that it's a product of these brackets. Now, because of the mass dimension, the number of momenta in the 3-point amplitude here and here is different. Here this is a mass dimension 1 as these 2 amplitudes for spin 1, and this is a mass dimension 3. It's obvious that if we take this amplitude calculated in Young-Mills theory and plot all the helicities to be minus, we cannot get this expression. But at the same time, this is the only possible expression for this 3-point amplitude. There cannot be any other one, because this was derived independent on the theory. This was just from helicity. Which means that in the Young-Mills theory, the 3-point amplitude with all helicities being minus or all helicities being plus, must be necessarily 0. Yeah, so in the Yang-Mills, despite it's not obvious just from this form in terms of epsilons and p's, you put 3 minuses, you get 0. You put 2 minuses and 1 plus, you get this amplitude. Yeah. Now, this means that if we want to find this amplitude in some theory, it must be a different theory. It cannot be Yang-Mills theory. Yeah. And does anybody have any idea what the Lagrangian for the theory for which this is a 3-point amplitude can be? F cubed. Yeah. So then in that case, if you take Lagrangian to be F cubed, you can calculate from that, again, amplitude in terms of polarizations and momenta. Now, based on the power counting, this will have 3 derivatives, so 3 insertions of momenta in the amplitude. So it has a mass dimension 3, as this mass dimension. In this amplitude, you put 3 minuses, you get this expression. In this amplitude, you get 2 minuses and 1 plus, and you get 0. Because in this theory, these amplitudes don't exist. Yeah, they exist here, but they don't exist here. Yeah. Yes. 2 extra what? If you even take more covariant derivatives. F, df, df. Yeah, so all 3-point amplitudes are 0. Yeah, on shell. So if you do it in terms of course, if you do it here in terms of epsilon and p's, you find some non-zero expression, but it will be proportional to p square. So on shell, it's 0. If you put it on Feynman diagrams on some internal line, you get non-zero. But it just means that you can always use equations of motions to push it from 3-point to 4-point and higher. Yeah. So this is good thing to remember that here the statements were independent on the theory. Of course, we can then look in which theory these amplitudes are actually realized, but we did it in the opposite way. We didn't start with the theory and then calculated the amplitudes. They were given to us. Okay, so this is about 3-point. So the 3-point kinematics is very restrictive. Let's now discuss 4-point amplitudes. And for 4-point amplitudes, this and higher as well, this rigidity is not there. Yeah? For 4-point amplitudes, we can define Mandelstam variables, kinematical invariants. We have 3 of them, S, T, and U, S being P1 plus P2 square. We already wrote that this is equal to, in spinor helicity, the product of 1, 2, 1, 2. But because of momentum conservation, this is also equal to P3 plus P4 square. So at the same time, you can also write it as product of 3, 4, and 3, 4. Yeah? Does that make sense? You can use momentum conservation to rewrite P1 plus P2 as minus P3 minus P4 and square it. You have also T. Yeah, in literature, there are different definitions of T and U. Sometimes they are flipped. I use this definition of T. Maybe you learned the other one. But and here it's 1, 4, 1, 4, but you can also write it as P2 plus P3. So this is also equal to 2, 3, 2, 3. This will be special. These relations are special for 4-point kinematics. Yeah. At 5-point, you will not have such relations anymore. Yeah. But here we are using the fact that P1 plus P2 plus P3 plus P4 is 0. There is a momentum conservation. So many things are equal, yeah, like here. And then U, P1 plus P3 square, which you can also. Now, I made a statement that it's important that the kinematics factorizes. We will just see it in a second, the importance of that. Now, the S, T, and U, they are not independent. They satisfy the relation S plus T plus U is 0. Maybe you learned in the QFT they are also equal to the squares of masses, but the masses are all 0. So the right-hand side is just 0. Okay, very good. Now, once we write the 4-point amplitudes, they can depend on this ST and U. So obviously, they are not completely fixed, because you can have expression like S over T, which has no mass dimension, no little group weight. So the constraints that we use at 3-point are not sensitive to it, if it is present or not. Yeah. Okay, but what can we tell about 4-point and then potentially higher? So there is an important condition that the 4-point amplitude satisfy, and this is factorization. The factorization property tells us that the 4-point amplitude must factorize into a product of 3-point amplitudes on the special kinematics. So if we send S to 0, the 4-point amplitude must factorize into a product of 3-point amplitudes. So it must be equal to A3. This is just schematic. We will make it more precise. Over S. Yeah, it blows up. There is a pole in S. It blows up. And the residue is the factorization into two 3-point amplitudes. And similar on other channels too. Yeah. Okay, so this is schematically the statement about factorization. But now, as I indicated already, as I indicated here, the S equals 0 is not a single condition. Yeah, you have to decide how do you set things to 0. So we will dive more into the details of how it works. Yeah, but now the property of factorization actually applies to higher point as well. This is not something special for 4-point. So we have an n-point amplitude. If you sit on a pole of that amplitude, yeah. So here I have to already say that we are working at 3 level. Yeah. So this is a factorization statement at 3 level. We said at 3-point the loop order didn't matter. This was just fixed. Yeah, maybe some overall factor might depend on some loop information and so on. But here, starting at 4-point, the loop order is important. Yeah, the 1 loop amplitudes are, and 2 loop amplitude and so on are more complicated. So here we are working here at 3 level. So the 4-point amplitude factorizes into a product of 2 3-point. The higher point amplitude in general factorizes into a product of 2 lower point amplitudes, where now S is not the S, the 4-point S, but some higher point Mandelstam variable, the sum of momenta. So we typically draw these factorization diagrams. Yeah, it means that if the S is 0, where S is now a sum of momenta on one side, square of that, then the amplitude factorizes. Yeah, this is also called 3-level unitarity, because this is a property of the unitarity of the amplitude applied to a 3 level. Yeah, so the factorization. So we will call it factorization, or sometimes it's also called it 3-level unitarity. Okay. So let's now look more concretely how things work at 4-point, and how does this factorization look like? How does it look like in details? Yeah, we just schematically saw that things must factorize into the product of 2 3-point amplitudes on a pole when one of the Mandelstam invariants, one of these ST and U are 0. But how does the factorization look in details also with respect to these spinor helicity variables? Any questions? Yeah. This is also true for massive, yeah. So So instead of, yeah, I just wanted to say it now, but let me already mention here, the fact that S is 0 means that this line is on shell. Yeah, normally, let's say in Feynman diagrams, you would like diagrams like that, but the internal lines are these virtual particles, how it's standardly referred to, and these are off shell. But if you sit on a pole, set S to 0, the S is 0, makes this p square equal to 0 on shell. Yeah, so now think this internal line is on shell, and therefore these two free-point amplitudes are on shell now. Yeah. If you have massive particles, the only difference is that you will have p square is m square, not 0. Yeah, but the factorization works as well. So from the unitarity, there is a real detailed argument how it comes from that. From the unitarity, you basically start with S dagger S is 1. You expand S in the perturbation theory, and you will find that, that at tree level, this implies the factorization into two tree-level amplitude. Then you will see also analogs at loops, yeah, what the unitarity applies to loops, unitarity cuts that we will talk about today. Yeah, we will now go into this argument, but the statement here, you can actually even see it in Feynman diagrams. If you assume that the amplitude, yeah, it's little now, I don't want to use the Feynman diagrams, but sometimes it's good to have it in back of your mind to kind of prove certain statements which come just from QFT in general directly at the level of Feynman diagrams. If you consider all Feynman diagrams, you look at one given propagator in all Feynman diagrams and you put it on shell. Yeah, you look at this propagator, there is this virtual particle that doesn't exist, but you say that p square is 0. So it's on shell. Now, all Feynman diagrams just split into two sets, and on both sides, you reconstruct the tree-level amplitude. Yeah, so you can actually see this, this factorization statement at the level of Feynman diagrams. Okay, good. So let me repeat it again. So we have a 4-point amplitude. Now we set S equals 0. And now we have to decide if we set to 0 this factor or this factor. So let's consider we set to 0 this factor. Yeah, and then we will do the other one. There are two solutions. Yeah, so there are two solutions to S equals 0 factorization. So this is first solution. Yeah. What happens is that the amplitude must factorize into two 3-point amplitudes. And here, this is now on-shell particle. Yeah, it's an on-shell state with p square equals 0. So this is an on-shell 3-point amplitude, and this is an on-shell 3-point amplitude. And we already know a lot about 3-point amplitudes. They are just completely fixed. They are independent on the theory, just from the spins. Okay? So let me assign some helicities to these particles. Let's say we have 1 minus, 2 minus, 3 plus, 4 plus. Example, yeah, this is just example. Then we are sending S to 0. So P1 plus P2 square is 0. So this is exactly the momentum of this internal particle. It's P1 plus P2, or minus P1, minus P2. Yeah, the opposite sign. Yeah. So this internal particle, let me call it P. So P is, if all things are incoming, is minus P1 minus P2. If we consider this direction, which is equal to P3 plus P4, but it's on shell. Yeah, P square is 0. Yeah, P square is 0 is exactly S is 0. Yeah. Does that make sense? Questions? Yeah. And now I erase it just here. So because we are sending 1 to square bracket to 0, the 3-point amplitude which shows up here is the one where all the lambda tildes are proportional. Lambda tilde 1 is proportional to lambda tilde 2, and it's proportional to lambda tilde of our physical on-shell particle, which we just created here on the pole. So this is a 3-point amplitude, the white vertex. And here, the 1, 2 to 0 also forces the square, the angle bracket 3, 4 to 0. Yeah. So we said that this is equal to that. The kinematic says that if you set this to 0, you at the same time set this to 0. These are the same conditions. This is special for 4-point kinematics, yeah, because we just have many conditions between that. So 3, 4, lambda 3 is proportional to lambda 4, and this is proportional to the internal lambda, which flows here. The 3-point amplitude is this black vertex here. Okay, so starting with 4-point amplitude, which has 4 external on-shell legs, we are sitting on a pole S is 0. The whole thing factorizes into a product of 2 3 points with on-shell internal particle. And these 3-point amplitudes are the one with the white vertex, the other one with the black, which comes from this kinematics, because we forced the lambda tildes of these two being proportional. That created us the 3-point amplitude white one here. And the same thing happened on the other side with just lambdas. 3 and 4 were proportional, and also proportional to the lambda of this internal particle. And that was a black vertex. This is a slightly, yeah, this is a real kind of new, slightly more complicated argument. So it's important to ask questions if you have any. Yeah, okay, I see where somebody starts. Oh, okay, good. So it's actually, yeah, one way how to see it is from here. Yeah, because, okay, so let me. So if we set S to 0, we have two solutions. 1, 2 is 0, or 1, 2 is 0. Okay? In that case, the 4-point kinematics now starts to factorize into two sets. Yeah? Here it says that lambda 1 is proportional to lambda 2, and here it says that the lambda 1 tilde is proportional to lambda 2 tilde. Okay? And the amplitude will factorize. So we will have 1, 2. Okay, in that case, this would be black. Yeah. And there would be an internal line, and P1 plus P2 will be the momentum of this internal line, and this is the same thing as up to a sine P3 plus P4. Sorry, well, this will be white. But here in this vertex, the lambda tildes will be proportional, 3 and 4. Yeah? But this is the same condition as this condition, because we just imposed one condition, not two. This was one condition, set this to 0, and this was kind of an accidental relation. Yeah? It was a consequence of this first condition, yeah? Being this set to 0. Yes? Yeah, that you actually, okay, so that's a kinematical exercise that you can do. We will not do it here. You start with 4-point kinematics. So you have this condition, then you have the squares of that are 0. You send this to 0, and you will see, so yeah, relatively easy calculation, but if you take a bit, and from that it will imply that this is 0 as well. Okay, so we will leave it as an exercise. I will not do it here. But there is a physics argument of the 3-point amplitudes, but there is just a purely kinematical argument that independent of any amplitude, you can see that having this to 0 and having all momenta on shell to 0, imposing this implies this as well. Okay. Okay, good. So let's more questions. So this was about kinematics. Okay, I will continue. I will erase this and continue here. And this statement is also true at other channels as well. Yeah. So the amplitude must satisfy this condition. There also is another solution for S is 0 when the thing that we are setting to 0 is 1, 2, and 3, 4. Yeah. And then the amplitude must factorize again like this. And for now sending this bracket to 0. Yeah, there is there will be a okay, so maybe before I have to also state here one thing, yeah, because that's important for the other discussion. Now this particle is on shell. We have to take it now seriously, like the external particle here. So it also has helicities. Yeah. So before it was a virtual particle, we couldn't talk about helicity of that particle. But now it's on shell. We can talk about helicity of that particle. Okay. And now we have this assignment that these two helicities were minus, these two were plus, and they were meeting in this vertex and this vertex. We already set what are the helicities in this vertex for 3-point amplitudes. This corresponds to minus, minus, plus. So the helicity of the internal particle here must be plus, and on the other side, it's minus, which corresponds to a vertex minus, plus, plus. Yeah, so this momentum flows from here to here. On the one side has minus, on the other side has plus, because here it's kind of outgoing, here it's incoming. So the helicity flips from incoming to outgoing. Does that make sense? This is now a physical particle. It has a helicity. Now, you can ask what would happen if there are more options. Suppose that here the helicity was fixed from this vertex and this vertex. But there can be other helicity assignments. So maybe let's do it now to make this clear. So sorry, I'm now erasing that. What about the amplitude, which was 1 minus 2 plus 3 minus 4 plus? So on the same pole, we had 1 minus 2 plus, and here we have 3 minus 4 plus. Okay, and this is again an internal on-shell particle. Now here we have minus plus, so here the helicity here had to be minus, and here had to be plus. Okay, does it make sense? So so the helicity of this particle was fixed by demanding that in the white vertex we have minus, minus, plus, and in the black vertex we have plus, plus, minus. Yes? No, this is not even assuming Young-Mills. Yeah. Okay, right. Yeah, so this is assuming, good. So here the helicity could be minus. If we were not at this minimal theory, the Young-Mills, good. So this would be in Young-Mills. If you have another theory where the fundamental vertex is minus, 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 yeah, indeed, then this would be minus and this would be plus. Yeah. So these assignments are in Young-Mills theory, or general, if you have higher spins, because we didn't specify spin is 1, it would be when we have minimal, so-called minimal coupling. The number of derivatives is minimal. But if you know what are your fundamental vertices, with pluses and minuses, then you can always fix what are the amplitudes in this picture. Okay, so let's write it explicitly now. So our amplitude (1 minus 2 minus 3 plus 4 plus) on the s equals 0 pole, when we made the first choice, but there will be for 1, 2, and 3, 4 is 0, factorized into 3-point amplitude, which had helicities 1 minus, 2 minus, and p plus. P is this internal on-shell leg. And the other one was 3-point amplitude with p minus, 3 plus, and 4 plus. Okay? But this already tells us something. We don't know how the 4-point amplitude looks like. I haven't written it. We haven't calculated it. But even if we don't know what this 4-point amplitude is, we already know that on the pole, it must be product of 3-point amplitudes, and we know the 3-point amplitudes. So we have some information. Yeah? We know how the amplitude behaves on the pole, yeah? Despite we don't know what it is. Yeah? And these 3-point amplitudes are fixed. Yeah? We wrote the formulas for them. Okay, so we learned something. We haven't learned everything, but we learned something. Okay. Now you can ask, what about the other solution to the S-pole? So the second solution to S is 0, that was 1, 2, and 3, 4. So that's what I started to write there. Sorry, I made a small detour before. Okay, so what can we learn here? So things must again factorize. Now, there is 1 minus, 2 minus here. And this is the angle bracket being sent to 0. So the amplitude which must sit here is the black vertex, right? However, for the black vertex, the associated helicities were minus, plus, plus. 2 pluses and 1 minus. This is already a violation of this. Okay? Yeah. So there is no helicity assignment which would make it work. Which just means that the amplitude doesn't have this pole. Yeah? No such pole. Because we cannot construct this picture from that. But this picture was given to us. Yeah, it had to factorize like that on the pole, but the kinematics was in conflict with the helicity assignments. If we flip the minus to plus, we could do it. Yeah, we could put plus here. Yeah, so if the amplitude was this other helicity assignment, I wrote there. So if we had then on 1, 2, 3, 4 is 0, we could do it. We just have to put plus here and minus here, and everything is consistent. Yeah. there is a pole, and it must factorize. Using this, the picture gives you how it factorizes. Okay, any questions about this? Yes? Right, so this tells you that 1 and 2 lambdas are proportional. And they will be proportional to the lambda of the internal line as well. But this solution, this kinematic solution, only corresponds to amplitudes which have assignment minus plus plus or plus plus plus. Yeah, in case we are not in this minimal coupling, but we have higher derivatives. But this is in violation with already having 2 minuses. So such an amplitude doesn't exist, and the factorization doesn't exist. So there is no pole, yeah, here. While this amplitude has a correct assignment with putting plus here, so then it must factorize on this pole like this. Okay? So this Helicity assignment already tells us which poles are there and how it factorizes. Okay? So here we did it only with S pole. We can repeat the exercise with the T pole and U pole as well. It will be the same. You just flip some labels here, yeah. So same for T and U poles. So here, we still haven't constructed any 4-point amplitude, but we already learned about factorizations of the 4-point amplitude. Yeah. It must factorize like that. There is just no option. Any questions? So if this is clear, we will now construct the 4-point amplitude. Question on the... Okay, no questions on the Zoom. Just... So here I didn't specify what these 3-point amplitudes are. Yeah, it was could be general spin S. Yeah, the only thing which was kind of the input is saying which amplitudes are in our theory are these minus, 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 plus, or the 3 minuses. Yeah, but for example, the factorization, if the factorization exists, and for example, here you work with spin 1 and F cube theory, it's just, this amplitude is just 0. Yeah, it's kind of a dumb, trivial statement. It means that the factorization in principle exists, but the 3-point amplitude is in fact 0. Yeah. If you work in the Young-Mills, the amplitude would be non-zero. Yeah. So you can also say that in Young-Mills, the all minus amplitude exists, and all plus, just the coupling in front of it is 0, happens to be 0. Yeah. No. This is that's what I said. I didn't specify the spins here. Yeah. Didn't specify the spins. It can be spin 2, spin 3. Yeah. We will exactly now deal with the spins. Yeah. We will now answer the question, what are the allowed spins? Yeah. So far, everything was allowed. As we discussed at 3-point, any spin is allowed, no restriction. Now we go to 4-point, and we will see that the 4-point amplitudes already gives us a huge restriction of what types of spins we can have. So 4-point amplitudes, in particular, we would like to answer the question, what are allowed spins which factorize properly, yeah, which satisfy these factorization statements. Okay, so what do we know? So let's now consider the spin S. So we know that the 3-point amplitude for spin S, if we have 1 minus, 2 minus, 3 plus, this is just repeat, was 1, 2 cube over 2, 3, 1, 3 to the S. And the other one, 1 plus, 2 plus, 3 minus was 1, 2 cube over 2, 3, 1, 3 to raised to power of S. So now the only thing that I assume is that these are the only So we are in this minimal coupling. So we don't have the all plus or all minus amplitudes. We can run the argument with that as well, but it will go similarly. But we've assumed that we are in this minimal coupling. So we have no minus, 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 or plus, plus, plus. Yeah, the only amplitudes are minus, minus, plus, and plus, plus, minus. And the relabelings of that. So these are our 3-point amplitudes. So now we consider a 4-point amplitude for spin S. So now the 4-point amplitude on the S pole by, again, picking the 1, 2, 3, 4 solution. The 4-point amplitude has an assignment, the 1 minus, 2 minus, 3 plus, 4 plus, but it's a spin S, yeah, not necessarily spin 1. So on this S pole, it must factorize from what we had before as 1 over S, that's the pole, times 3-point amplitude. So I draw the picture here again. So this is plus, minus, plus, plus. This we denote P. So it's an amplitude 1 minus, 2 minus, P plus, times the amplitude P minus, 3 plus, 4 plus. And we can plug for these formulas. Yeah, we just have to relabel. Yeah, we have to relabel things to match the labels of that. So this is 1 over S. The 3-point amplitude here is 1, 2 cube over 1p, 2p, to S times 3, 4 cube over 3p, 4p to S. Any questions? Yes. Okay, so good. So here I assume that it's spin S. The argument is kind of cleanest here. You can also assume different spins. Yeah, the argument is just more detailed. There are many cases to consider, but the conclusion of what I want to say will apply even if there are like combinations of different spins. Yeah. As I said, the conclusion, I can tell you in advance, the conclusion is there are no higher spins. Yeah, and that conclusion you can also reach in case you don't consider the same spins in the beginning. You say that some of them are 0, 1/2, 1 up to S, but you will still rule out the high S. But then you have to consider many cases. Here, if we assume that all particles have the same spin S, then we will have a very simple, clean argument. Yeah, we are not, this doesn't prove that everything is not allowed, but at least we will be proved that interacting spin 3 theory is not allowed, or spin 4, spin 5, when no other particles are involved. Yeah, from this argument. But as I said, the argument generalizes. There are papers who did it really in details. But here we consider just single spin S. Okay. So let's continue our calculation. So on the pole, it's not equal, sorry. I have to be here specific. On this pole, we will have 1 over S. And then I just put these brackets together. We will have 1, 2 cube, 3, 4 cube, 1p, 2p, 3p, 4p, raised to power of S. Okay, now we don't know what is lambda. We don't know what is lambda p and lambda p tilde. In order to calculate the amplitude, we have to calculate it, which is possible. We can calculate it from these conditions. There is a momentum conservation in each vertex. The lambda tildes here are proportional. Here the lambdas are proportional, so we can calculate it. But there is a small kinematical trick that we can use. So I will just show you how the trick goes. It's always better to make life easier. We can just pair this bracket, let's say with this bracket, 3p, up to a minus sign. This is equal to this. Okay? And this thing together in the middle is nothing else than the momentum p. Yeah, this is lambda p tilde. So this is exactly this mixed bracket I was telling you before. So we can write it like that. The p, the A index is dotted with lambda 1, and the A dot index is contracted with lambda 3 tilde. But P is nothing else than P1 plus P2. Okay, so we can just plug 1 plus 2 here for that. Yeah. So this is just equal to 1, and I write it as 1 plus 2. But lambda 1 dotted with lambda 1 is 0. Yeah. So this disappears. So this is just equal to 1, 2, 2, 3. The product of these two brackets. Does that make sense? So we combine that into P. The P is equal to P1 plus P2. We plug it here. We basically rewrote this as 1, 1, 1, 3, but 1, 1 is 0, the angle bracket, plus 1, 2, 2, 3. That one state that is non-zero. Yeah, it's just a small kind of trick. Otherwise, we can just solve for lambda p and lambda p tilde from that picture and plug it here. So similarly, we can pair 2p and 4p. Yeah, sorry, there was a minus sign. I just forgot minus sign here. And then we will get minus 1, 2. So say maybe what I want to write 1, 2, 3. Yeah, I would like to write it like that. 2, 3, 3, 4. Yeah, so that's a small exercise you can do. You can again pair it. P is equal to P1 plus P2. It's also equal to minus P3 minus P4. You actually plug it here for P, and you get 2, 3 bracket and 3, 4 bracket. There are more ways how to write it exactly because we have a relation between P1 angle bracket. We have this relation as well as similar relations. So there is always some ambiguity how you write it. They are kind of all equivalent. Anyway, after we plug back for these things which depend on P.
Professor.
Yes.
On this side, rigorously, we would have to write P3 and P4, right?
This?
Yes.
Yes.
So we wouldn't have those minus signs. At the end of the day, we have two minus signs, we'll cancel out, but the right way to write wouldn't be P3 and P4 on this side, so we don't have to do this kind of change.
Sorry, are you worried about the minus signs?
No, I'm just asking if it's okay to write this way.
So we have to plug for these guys. Yeah, so we can either just solve for lambda p and lambda p tilde and plug it there. That's one option. It's possible, it's perfectly fine. I'm just using like a short trick which doesn't solve for them individually, but we realize that they appear in a combination of lambda p tilde, which forms together a momentum p. And the momentum p we know, because this is just sum of P1 plus P2 or P3 plus P4 up to a sign. So we are using that and just plugging for P here directly for 1 and 2 or 3 and 4 and evaluating this product, this expression. And so we paired this with this and this with this. We could also pair it oppositely. We will get the same result. Yeah. So yeah, this is not like a fundamental way how to do it. It's just a small trick to it's very useful in these calculations. So I wanted to show it to you. Okay, so what we get is a 4 on this S channel is equal to 1 over S. And we assemble what we got here. Is divided by 1, 2, 2, 3, and 2, 3, 3, 4. The minus signs canceled. We had no signs here. Okay, to the S. Okay, so 1, 2, 1, 2 cube. So this cancels, this put square. 3, 4 cancels, put square. And this product is equal to T. Okay, so the result is that what we got is something which depends on helicity. And then factor which only depends on S and T. The thing is 1 over S, S is 0, we are sitting on that pole, times T to the S. Yeah, sorry, this S is a different than this. This is a spin, this is a Mandelstam. Yeah. Yes? Yeah, okay. Yeah, it is minus P. Yeah, it's minus P. It's not analytically continuous. Yeah, one is them is P and the other one is minus P. Right. So they appear in pairs, so it doesn't matter. Yeah. So if there are certain cases when you have to be careful about the sign. Yeah. Here they always appear in pair. So here we are sloppy. Let's say it like that. We are sloppy about the sign and it works. You can do it carefully, but here you don't have to because things appear in pairs. Yeah. The sign here doesn't appear. We can also then this square also put here in the exponent. So we have this to the S here. Okay, does this result make sense? So on a S equals 0 pole, we got this result. This is how the 4-point amplitude. We still don't know what the 4-point amplitude is, but it must be equal to this when evaluate on S equals 0 pole. Okay, and now we can do the same thing with the other poles. The T equals 0 pole and U equals 0 pole. So we get 3 different conditions. So on all 3 poles, so on S equals 0 pole, the amplitude behaves as 1, 2, 3, 4 to 2S times 1 over S and T. And let me say that this is the S for spin, so that we just don't confuse the Mandelstam and the spin. If we do T equals 0, we will repeat exactly the same exercise. This factor which carries helicity will be the same. So in this logic, we put this new S here. And this will be S to the S. And the U equals 0 will have the same prefactor. and this will be multiplied by 1 over u times t to the s. Now note that we had this relation s plus t plus u is 0. So one of the variables is always redundant. So for example, on s equals 0 pole, t is equal to minus u. So there are kind of more ways how to write these expressions. These expressions are on the poles, right? Yes? Right, right, good, good. So we had this other, so this was one of the choices.
Sorry, can you repeat the question?
Yeah, okay. So there was a question, we only did the analysis for one of the choice, for s equals 0. There was this other choice. This other choice for this helicity gave no result, so there was no pole, right? So that would be, the similar analysis will be for the other poles. The thing is that for both of the choices, suppose that they were both allowed, they would give the same result here. So I'm just telling you, but one needs to check. Yeah, it's something to check as well for both choices in principle. Okay, so this is our constraints. Yeah, so this must be true for any spin, or for any amplitude, for any 4-point amplitude with spin s. It doesn't matter in which theory we are working. This was just a consequence of factorization and 3-point amplitudes. Yes? Massless, massless, everything is massless. In our discussion, everything is massless. Okay, but here is the problem now. You can check, or you can easily argue, that if you want just to satisfy this statement on an S-pole, I can do it for any spin. Yeah, I can just declare that the 4-point amplitude is this expression, literally. Not on the pole, but for general kinematics. So it's this factor, which we'll repeat here, times 1 over s to the t to the s. That is my amplitude. It satisfies this expression on the s-pole. But if I do it, it will fail to satisfy this expression on the t-pole, because for higher spin, there is a t to the higher power. But we know that the t-pole is only first power. So this is in conflict for general s. And similarly, if I start with the t-pole, I have s to some higher power. And this is incompatible with the s-pole. So I'm start to get a restriction on what the s might be. And you can see that the problem is there are only two solutions here. Yeah, some people might object. I will correct it or supplement it just in a second. But if I demand these three factorizations, then we get only two solutions for spins. Yes?
Can you repeat why are you saying that you demand that your solution is the first line for whatever s?
So, okay, so our 4-point amplitude must satisfy all three statements. Yeah, on S-pole, it must behave like this. On T-pole, must behave like this. On U-pole, it must behave like that. It's not optional. Yeah, this must be that. Now, you can ask, does there exist such an amplitude which behaves like that? I am saying that if the spin S is high, you have a problem. Because on the S-pole, you generate 1 over S times t to the s. Let's say t squared, t cubed, t to the 4. But this expression is OK on an S-pole, but it's wrong on the T-pole. Because this is t to the higher power, but I need t to the first power. I cannot have a higher pole in the amplitude. Okay, so they seem to be in conflict with each other. So the only two solutions I can get. So this is a restriction on spin.
Sorry, I have a question.
Yeah.
Is it necessary to have like equal amplitudes for s equal to 0? And suppose you have t square for s equal to 0 and just t for t equal to 0? Is it?
No, but let's just try it. Yeah. So suppose that the amplitude. Okay. Let's test. So the amplitude would be this Helicity factor. You see that this Helicity factor doesn't play any role. It's always sitting in front. But then the amplitude, let's say, would be 1 over s times t to the 5. Yeah, so this is for spin 5. This expression factorizes well on an s pole. It does what we want. But on the t pole, there is t to the 5. That cannot be there. There should be a single pole in t. So now you violate the second condition. This is not a good amplitude. Yeah, and that's the problem. You need only the first power of t. Yeah. Well, let's see. Okay, let's see. Good. So you can just enumerate the s's and ask, is there a consistent amplitude for a fixed s? And you get only 2 solutions. The first one is spin 0. Yeah. So the spin 0 amplitude would look like this. The s is 0, so the prefactor is actually 1. It's this thing. And the amplitude is just 1 over s plus 1 over t plus 1 over u. You can quickly see that it satisfies all 3 conditions because s is 0. The 3 poles just don't talk to each other. You just sum all of them. And this is nothing else than phi cube theory. So self-interacting scalar particle is consistent. Okay, we haven't learned any breakthrough discovery, but it's fine. It passes our check. The only second solution that we get is actually spin 2. In that case, the amplitude is this prefactor times 1 over STU. On an S pole, T and U become the same, and you get T squared, up to a sign. I said I was a swap pair both signs. On the T pole, S and U are the same, and you get S squared, or U squared. And the same thing on the U pole. Yeah? So this expression satisfies all 3 conditions. Okay? And this is an amplitude in GR. 4-point amplitude. Yes? Spin 0. Sorry, say it again.
Just for instance, if you pick spin equal to 2.
2, yes.
And the S pole, so big S should be 0.
Yes.
But you're dividing by 0. Like,
no, so you are sitting on the S pole, and you should generate the factor 1 over T squared.
Yeah, I mean, I'm talking
no,
about...
sorry. Well, we said that this is spin, this calligraphic S.
Yes.
And the normal S, unless I screwed up something, is the Mandelstam. And calligraphic is spin.
But well, my question is for like the amplitude for the GR that you talked about, right?
Yeah.
So if I choose to be on the big S pole, so big S equal to 0.
Yes.
But you're dividing by 0 there, so I mean, what's...
No, it's a pole. The amplitude has a pole.
Yes, sure.
There is 1 over S. It blows up.
Sure.
The amplitude blows up, but on the pole, you should generate T squared.
Okay.
That was what we got from this very general discussion of 3-point amplitude. You should generate 1 over T squared. And you do generate it because you have 1 over T times U, but on that pole, T is U. So you do generate 1 over T squared. And the same thing on all the other 2 poles.
All right.
Yeah? So it passes all 3 checks for spin 2. Once you go to spin 3, you fail to satisfy it. Yeah, there is just no such a function. Okay, extremely, great question. What about spin 1? Yeah, we have an interacting spin 1 theory. So what about that? It's not in our list. Well, why it's not in our list? So let me just show what the amplitude can be. So if I directly just do the extrapolation of what we had here, So what about the amplitude is something like this, which would make good sense. So it's this prefactor to square. And then it looks like that I can write that. Yeah, because on each pole, on an S pole, I should generate 1 over T, which is the same thing as 1 over U. On a T pole, 1 over S, and so on. You see that there is something fishy here because S is here, there is 1 over T, 1 over U. Maybe I should put some 1/2 or something like that. The problem is that if you put it under common denominator, this amplitude is S plus T plus U, which is 0. So we don't have this problem with higher poles, but the only reasonable thing that we can write is 0. Which means there is no self-interacting spin 1 theory if we don't dress it with something else. In other words, we just ruled out the photonic self-interaction. So there is no photonic 3-point amplitude. Sorry, 4-point amplitude. When we would have like interaction of photons, like that. Okay? But no, 5 to the 4. Okay, good. Here we assume that the elementary interactions are 3-point. Yeah. So if you start with 4-point, you have to make an argument with factorization, let's say 6-point amplitude into 4-point amplitudes, and so on. Here we assume that the elementary interactions are 3-point interactions. Yeah. Of course, we don't rule out the existence of the 5 to the 4, but that doesn't have any poles. So the elementary amplitudes are 4-point. Yeah.
Sorry.
Okay, we are not done with spin 1, by the way. Yeah. Yes, questions.
Yeah, sorry, one more question. So you said there is no photonic 4-point, but what about gluonic? Like
Exactly. That's a great question. But for gluons, we have to do something a little bit more. Yeah. So for gluons, the factorizations were not exactly what I wrote. Yeah. There was one piece missing, and there were the structure constants. Yeah. So if we allow to dress the 3-point amplitudes with some extra factor, which carries some groups, then the discussion is different. And the discussion is different because in this case, there are f's in the numerator, which obstructs this relation that it's 0. Yeah. So the gluons exist, or the gluonic amplitudes are consistent, and we just have to dress the 3-point amplitudes with some extra group structure. So then we get something like F A B E, E C D over S T plus F A D E, F B C E over S, I don't know, U, okay, F F over the last one. Okay, and this will factorize then properly, but this means that the 3-point amplitude that we started with was dressed with some factor FABC, but this just meant that we have multiple particles. Yeah, we have multiple gluons. Multiple spin 1. For single spin 1, we couldn't do it. We would run into this problem. But if you allow multiple of them, then you can do it. Now, with gravity, we didn't need it. We can do a single graviton. It's actually even opposite. If you run a little bit detailed argument, you can see that if you dress the 3-point graviton vertex with some f, you would like to do some non-abelian version of gravity, everything trivializes, and you just get like n non-interacting gravitons. Yeah. So this factorization argument, as the only solutions, going from 3-point to 4-point gives single scalar, single graviton, and multiple spin 1s, which are gluons. And nothing else is allowed. Yeah. Again, I ran the argument only for single spin, so now you can ask What about coupling this spin to this spin and so on? And then you can do a web of everything, but you still end up on having only spins 0, 1/2, 1, 3/2, and 2, while 2 must be gravity. 3/2, you even get that it must be gravitino. You must to couple it supersymmetrically to gravity. There is no other option. Nothing else factorizes correctly. And yeah, and then you get different constraints on also on spin halves and so on. Yeah. So, and this is just imposing factorization of 4-point amplitude into 3-point. Yeah. Not in flat space. Yeah, so if you don't, yeah, this is in flat space. Yeah, if you don't do flat space, if you do ADS, then of course the story is different. The 3-point amplitudes are not fixed, and yeah, things are different. Yeah, not fixed in this way. Yeah, you can have these Vasiliev theories and so on, but they are not in flat space. Yeah. So here we didn't assume anything like 1/2, 3/2. It was ruled out. But you don't have like a 3-point fermionic interaction. Yeah, that's also not allowed. So it's also not allowed here. Yeah, we didn't assume that this was integer. Yeah, we could go to a spin 1/2 solution, but we didn't. Yeah, but it makes sense. If you want to have fermions, you have to couple it, let's say, to photon to make it. Yeah, that you of course get as a solution to a problem. But for a single spin, these are the only allowed things. Okay, so so we ruled out the higher spins. They were allowed at 3-point, but they are not allowed at 4-point. They don't factorize correctly. What? For in? Yeah, the Born-Infeld has a 4-point coupling, right? Not 3-point. Yeah. So the 4-point amplitude is okay if it doesn't have to factorize into 3-point, which the Born-Infeld doesn't. Yeah, so yeah, this assumes that the fundamental interactions are 3-point. Yeah. Okay, good. So
yeah, I guess so it's time for questions.
So I didn't make it to color ordering. Yeah, so but we ended with gluons. Yeah, gluons are fine. But now we would like to calculate the amplitudes of gluons, and we will start with gluons the next lecture and basically do the gluons for the rest of, with some gravitons in the end. Yeah, there is also something interesting about phi cube amplitudes, but the real kind of mileage that we get from these two methods are for theories with spin. Spin 1, gluons, and spin 2, gravitons. Yeah, they are the most difficult in the standard approach in terms of Feynman diagrams, and they are the most beautiful in these more modern approaches. Okay, questions? Yeah.
Maybe wait for the microphone.
We are working with fundamental 3-point interactions,
yes.
But for the graviton case, we have also a fundamental 4-point interaction.
We have 3-point and 4-point. Also in Young-Mills, we have 3-point and 4. In gravity, we have infinite tower, actually, any number of points. Yeah.
So what about the amplitude that have no poles?
Well, it needs to have a pole. That's not optional. We have to write, once you have GR, you have 3-point interaction or Young-Mills, you have to write this factorization diagram. And the thing must factorize correctly here. Yeah, you cannot just pick your vertices that you want and forget the others. Yeah, you have to take all of them. Yeah, so it will have. You can ask, is there a theory with fundamental 4-point like Born-Infeld? There is. So this argument doesn't apply to Born-Infeld. You can have photonic interaction, but then the fundamental vertex would be 4-point, and you build 6-point amplitudes and higher from that. Yeah, that you can do. Yeah.
So does it mean if the fundamental interaction is 4-point, we can have like spin 3 particles?
No, you cannot. You can still rule it out, but then you have to do from 6-point to 4. You have to consider 6-point amplitudes and factorize them into 4-point amplitudes. By the way, the argument about non-existence of higher spin interactions is more subtle actually than that. The higher spin interactions are allowed, but you have to work not in the minimal coupling, not even the subminimal. You have to go to higher derivatives. Yeah. In other words, you can Yeah, if you have enough derivatives, I forgot what is exactly the bound, you can write interacting higher spin theory. Yeah, it is allowed, yeah. But not for the minimal coupling, and the theories with the minimal coupling are special, yeah. We would say that they are the fundamental ones, yeah. Yes?
Sorry, this might be a nitpick, but normally when one goes from s equals 0 to t equals 0, or when one permutes s and t, there's also a permutation of the labels from, I don't know if your convention is permuting 2 and 3 or permuting 2 and 4.
Yeah.
So why is the prefactor the same, the 1, 2, 3,
No,
4
the
brackets?
prefactor just depends on spin. Yeah, so we would have to run, we just look at the S channel, we would have to look at the T channel and do it properly. But you will see that we factorize the same prefactor. The reason why this is the same prefactor, this is the only thing which carries the right little group weights and doesn't have any poles. So we will always get it independent on which channel. It's always there, yeah.
Okay.
Yeah, because the one and 2 were minuses, 3 and 4 were pluses. We would have to write that. There will be just no other option, yeah. But in principle, you can calculate it, yeah, if you do it on the T and U channel, yeah.
This works for 5 dimensions, for 4 dimensions. So
Yeah.
suppose we have a theory in some higher dimensional case with some other spins, and we compactify to 4 dimensions. What should happen to the particles with different spin?
Well, this is a 4-dimensional argument, right? So the result here is that once you are in 4 dimensions, the particles are massless. That's important, yeah. Typically, if you do some compactification, you can get some mass, yeah. This doesn't apply for massive particles. Of course, the massive higher spin particles exist, yeah. The atoms exist, they have a huge spin, and so on, but they are all massive. So this is a state of massless particles, yeah. So whatever you do, starting from any space you want, you compactify, you get here. There is some cursed space, yeah, and so on. You compactify. You cannot land up on the massless higher spin particles. You just cannot, yeah, interacting.
Any further urgent questions?
Sorry. Can you repeat the problem of T and U channel for high spin? I can understand.
Okay, so the problem was the compatibility between different channels, yeah. So, okay, I'll just erase something here. So you need a function. Okay, you can forget this Helicity prefactor. You see that it's the same. So you can factor it out. But you need some function of S, T, and U. Let's say for spin 3, which on the S channel gives you 1 over S T cube. On the T channel gives you 1 over T S cube. And on the U channel gives you 1 over U S cube. Yeah, now we said that on each channel, the other 2 variables are the same. Yeah, so it's kind of how you write it exactly doesn't matter. On the U channel, S and T is the same. Yeah, so I can write T cube or S cube, yeah. Now, the problem is actually only with 2 channels. You can kind of forget even the third one, yeah. So on the S channel, you have 1 over ST to the cube. That cannot be the right solution because it has T to the cube. You need a single pole in T. The amplitude cannot have a higher pole. Yeah? It needs a single pole. So this function itself is fine on an S channel. It's not fine on a T channel. On a T channel, it should look like that. You will find no function of S and T and U, which on S channel looks like this, and on the T channel looks like that. Just no function exists. Yeah? So that's the problem. You can make the amplitude compatible with this condition or this condition, but you cannot make it compatible with both conditions at the same time. And you need to have the compatibility with, and you also need with that one, but the problem is already the compatibility of the first 2. Yeah, the only thing that you get is this spin 0 and 2. Then you can make it happen. And with spin 1, you can make it happen if you add some extra group structure, which basically obstructs your amplitude to be 0. Yeah, because here you make it compatible, but the amplitude just happens to be 0 at the same time. Adding adding this group structure abstracts to being at 0, and then it's equal to the gluonic amplitude.
All right, so I suggest that if you have further questions, you can ask them in private or move them to the exercise/discussion session this afternoon. So let's thank her again.